All right, today we're diving deep into something called formal semantics. Now, this is a field that's all about tackling a huge question in computer science. What does our code actually mean? I mean, really mean. Let's get into it.
No, seriously, think about it. When you sit down and write a line of code, you've got an idea in your head, right? But how can you be absolutely 100% certain that the computer is going to see it the exact same way you do? How do we pin down the real meaning of computation itself?
And this really gets at the heart of a classic tension: syntax versus semantics. Syntax is just the grammar, the rules for putting the symbols together. So x equals y plus 1, yeah, that looks right syntactically. But the semantics, that's the big question. What does that line of code do? What changes in the machine's memory? That's the puzzle formal semantics is trying to solve.
So to get to the bottom of this, we're going to look at three main ways of thinking about it. First, there's operational semantics. That's all about how the code runs. Then we'll check out denotational semantics to figure out what it computes. And finally, axiomatic semantics, which is all about proving that the code is correct. Then we'll pull it all together and see why this whole quest for meaning is so important.
A really good way to wrap your head around this is to think of your program like it's a blueprint for some complex machine. And formal semantics, well, it gives us three totally different ways to read that blueprint. Each one gives us a unique and, honestly, super powerful perspective on what that machine is actually going to do.
All right, so let's jump into our first way of reading that blueprint: operational semantics. Think of this as the super detailed, step-by-step assembly manual for our machine.
So the core idea here is pretty straightforward. It's all about defining a program's meaning by describing exactly how it runs, one single step at a time. It's not really worried about the big picture outcome, but the nitty-gritty sequence of operations that gets you there.
And this quote really nails it. The source material calls it the stepwise behavior of a program. What that means is we're looking at the program like it's a system that just transitions. It moves from one state to the next, one instruction at a time.
And this is a perfect way to visualize it, right? You start in some initial state. Then, boom, the first instruction runs, and that pushes you into a new state. Then the second instruction runs, moving you to another new state, and on it goes. It's like a literal play-by-play recap of the entire computation.
Okay, so now for our second take on the blueprint. We're going to shift our focus from the how to the what. This is denotational semantics, and it's way less like an assembly manual and a lot more like a high-level performance model for our machine, describing what it actually achieves, not just the tiny steps inside. Instead of walking through the execution step by step, denotational semantics does something completely different. It defines the meaning of code by translating it into math. Pure abstract mathematics. Every single piece of your code gets mapped to a corresponding mathematical object, like a function.
So this is the key takeaway right here. We're assigning to every program an element of a mathematical structure. Your program stops being just a list of instructions to follow. It is, in its essence, a mathematical function. This gives us an incredibly powerful and abstract way to get at what it's all about.
But here's the real magic of this whole approach. It's compositional. What does that mean? It means the mathematical meaning of a huge complex program can be built up perfectly just by combining the mathematical meanings of its tiny little parts. It's just an incredibly elegant way to think about software. Okay, on to our third and final way of looking at the blueprint: axiomatic semantics. Now, this one isn't about how the machine is built or even what it computes. It's about proving that it's safe, that it's reliable. Think of these as the engineering safety guarantees. Axiomatic semantics comes at meaning through pure logic. Instead of trying to define what a program is, it defines what we can prove about it. It gives us a way to make logical statements about how a program will behave and then formally prove that those statements are absolutely true. And this quote just perfectly sums it up. It's a logical framework intended for reasoning about programs' properties. The goal isn't simulation, it's not a mathematical translation. The goal is proof. It's all about achieving total certainty. And the absolute cornerstone of this whole idea is something called the Hoare triple, which was pioneered by the great C.A.R. Hoare. It looks a bit technical, but it's a really simple and profound logical statement. It just says that if some precondition is true before you run the program, then you're guaranteed that a certain postcondition will be true after it's done. Now, this is incredibly useful for something called program verification. Proving that the software in critical systems like airplanes or medical devices is totally reliable. But there's a fascinating twist.
Thanks to Gödel's incompleteness theorem, we actually know that it's logically impossible to create a fully complete axiomatic system that can prove every single true thing about all programs. Kind of blows your mind, right?
Phew. Okay, so we've just looked at 3 really different ways to define what code means. So let's take a beat, put the complete blueprint back together, and see how these 3 different lenses give us a complete picture of a single program.
So, when you put it all together, you see we have 3 views that really complement each other. Operational semantics is our assembly manual. It tells us how a program runs. Denotational semantics is the performance model, defining what it computes mathematically. And finally, axiomatic semantics gives us the safety guarantees, proving the logical properties of that execution. 3 lenses, 1 program.
But that begs the question, right? Why do we even have 3 different approaches? And what's the end game here? Well, that brings us to the grand quest for unification, and why this stuff that seems super academic actually matters a whole lot.
See, computer science legends like C.A.R. Hoare, they had this incredible vision for the future, something they called unifying theories of programming. The goal was, and still is, to create a shared fundamental framework for understanding how all computer systems behave, kind of like how unifying theories in physics try to explain the entire universe.
And look, this is not just some theoretical daydream. We live in a world that is completely built on software. I'm talking about our banking systems, our power grids, everything. These formal methods are the best tools we have. They're what we use to make sure that the critical systems we rely on every single day are truly reliable, safe, and provably correct.
And that really leaves us with a final thought to chew on. The code we write is getting more and more complex by the day, and it's running more and more of our world. So that question that formal semantics asks, how can we be absolutely sure our code does what we mean for it to do? Well, it isn't academic anymore. It's one of the biggest, most important engineering challenges of our time.